Isaac Newton once famously said that if I have seen further, it is by standing on the shoulders of giants. Now, Isaac Newton was referring to the work done by other scientists before him that led him to give us the wonderful laws and theories that we study till this day. And of course, at the time, Newton himself did not know that he would go on to become the giant on whose shoulders other scientists would then stand upon. Now, the reason I'm quoting Newton to you at this juncture is because this chapter, which is the first chapter in your Physics Volume 1, this chapter, that is the physical world and measurement, is often mistaken to be an irrelevant or a useless chapter. However, the truth is that this is the kind of giant based on which you will be able to see the future of the understanding of physics. And therefore, I must take this point out and tell you that the physical world and measurement chapter is important to the understanding of physics, and you must pay careful attention to what you read inside this chapter. So let's begin our discussion with talking about the physical world first. Now, the word physics itself has its roots in different languages. In English, it is associated with physique, which means physical thing. In Latin, its roots come from physica. In Greek, it comes from the words physis, which means nature, or physika, meaning natural things. This means that physics is somehow related to natural things. In fact, by definition, physics is the branch of science which deals with the study of nature and natural phenomena. And therefore, because everything we see around us is what we call nature, it means that physics is helping us understand nature. And because everything is nature, it is inevitable that the study of physics will coincide with a large number of other studies. For example, the subjects of chemistry, engineering, astronomy, maths, and biology are all interconnected somehow with the study of physics. And therefore, no matter what you do, you cannot escape the science that is physics. All the phenomena that we see in our physical world can be explained with the help of four fundamental forces. The first of which is the most popular, that is gravitation. The force of gravitation, or simply the gravitational force, is the most common type of force that we have experienced in our lives from the very beginning of time. Gravitational force may be very weak as compared to the other three forces, but at the scale of the universe, it is the gravitational force that makes most of the decisions with respect to the different structures that we see in our cosmos. By definition, the gravitational force is the force of mutual attraction between two objects by virtue of their masses. These two objects can be anything as long as they have mass. In fact, it could be me and this fridge, and we both would still be experiencing the gravitational force because we both have mass. The next type of fundamental force is the electromagnetic force. It is the force which exists between the charged particles. For example, it is the force that exists between the proton and an electron inside a nucleus. But electromagnetic force is also associated with light, because light is an electromagnetic waves, and therefore the rainbow that we enjoy very well is also an example of the manifestation of the electromagnetic force. It also explains other physical phenomena that we see in our daily life, like friction, current, computers, lasers, lightning. All of these are related to the electromagnetic force. But inside the nucleus, protons and neutrons reside together. And we know that like charges repel each other, so all the protons should actually be repelling each other. And if they are repelling each other, how can they stay inside the nucleus? So obviously there has to be a different force which is forcing them to stay inside the nucleus, which will fight their electromagnetic repulsion. And this different force is the strong nuclear force. It is the force which binds the protons and neutrons inside a nucleus. And finally, the fourth type of force is the weak nuclear force. The weak nuclear force is associated only in certain nuclear processes, for example, such as beta decay of a nucleus. So these are the four fundamental forces that we see in nature. Now, in order to explain the natural phenomena that we see around us, scientists came up with what is known as physical laws. Now, even though these physical laws were given by scientists, the actual laws are obviously present in nature. And why do we need these physical laws? Physical laws are important tools in our investigation of nature. Now, you must have heard of the law of conservation of energy. We use that idea to solve different problems that we see in nature and find out something new using this law. Similarly, there are other laws, for example, the law of conservation of momentum, the law of conservation of mass, and so many others, including the Newton's laws that we have heard about in lower classes. Now, every time you see a physical law, you know that these laws are actually describing the relationship between different quantities, and these quantities are known as physical quantities. So here we are moving from the physical world into the idea of measurement. These physical quantities, by definition, are nothing but the quantities which can be measured, and with the help of these quantities, various physical phenomena around us can be explained, and then their relationship is written in the form of laws. Such a quantity which can be measured and is useful to us to write laws is known as a physical quantity. For example, if we take a look at Newton's second law, which we all know by now is F is equal to ma, then every single one of these symbols is actually representing a physical quantity, where F is a physical quantity called force, m stands for mass, and a stands for acceleration. All of these are physical quantities which we can measure, and they helped us write Newton's second law, which we know by now is extremely useful in explaining lots of motion around us. A physical quantity is represented completely by its magnitude and unit. Every time you want to talk or describe a physical quantity, you have to tell me about its magnitude and unit. And by now you know that the magnitude is just a number which tells us how many times into the unit that physical quantity lies. For example, if I say that I am buying 5 kg of sugar, what I am actually saying is that I need 5 bags of 1 kg sugar. And therefore 5 is the magnitude which tells me how many times into 1 kg must I add the sugar to get 5 kg of sugar. So in this case 5 is the magnitude and kg is the unit. So what exactly defines a unit? From here, we must understand that there are certain systems of units that everybody has decided upon. Scientists around the world have some standard units, and therefore they decide these units so that we can talk to each other. A unit decided by a scientist in India should be understandable to a unit decided by a scientist somewhere else in the world. And because of this, we decide on the systems of units. However, there isn't a single system of unit, there are many. For example, we have the first type, which is the CGS system. The CGS system is also known as the Gaussian system and is based upon the units of length, mass, and time. In the CGS system, the length unit is centimeter. That's where the C comes from. Similarly, the unit of mass is the gram, giving us the G, and the unit of time is the second, giving us the S. So centimeter, gram, second gives us the CGS system. Similarly, we have the MKS system. This is also known as the Georgi system. Now, the MKS system is also based upon the units of length, mass, and time. And under the MKS system, the unit of length is meter, giving us the M. The unit of mass is kilogram, giving us the K. And the unit of time is second, again giving us the S. So MKS is the meter, kilogram, and the second system. Finally, we have the FPS system, which is also known as the British Engineering System. In this case, again, the system is based upon the units of length, mass, and time. And here the unit of length is foot, giving us the F. The unit of mass is pound, giving us the P. And the unit of time is second, giving us the S. So this makes the FPS system. But the most widely accepted system of unit is the SI system. The SI system is the international system that is used by most of the scientists around the world. The SI system actually includes the MKS system. So they took all the units of the MKS system and added some more and made the SI system. So what are the quantities included in the SI system? The first quantity in the SI system is length. And the unit of the length which is included in SI system is meter, given by the symbol m. The next quantity is the quantity of mass. Now mass is given in terms of kilogram and therefore kg is the unit of the SI system. The next one is time, where second S is also a unit included in the SI system. So already you can see that length, mass, time, these three units, MKS, are already included in the SI system. But besides this MKS units, we also have other units. For example, the unit of electric current, that is ampere, is also included in the SI system. We have the unit of temperature, which is Kelvin, the unit of amount of substance or mole. This is what we use to measure the amount of atoms and molecules, and also the unit of luminous intensity, that is candela, given by the symbol CD. We also have two supplementary units. Those are the units of plane angle, which is measured in radians. This is the angle that we know very well. It is the angle that we measure in degrees, but the SI unit is the radian and not the degrees. However, there is also another supplementary unit, which is the solid angle. The solid angle actually describes the angular 3D volume of the same angle which we see on a 2D plane. The same angle in a 3D version is the solid angle, and the unit of solid angle in the SI system is the steradian, and the symbol is SR. So these are the different units in the SI system. So we understood what are the systems of units, and after studying the systems of units, there is one other classification that we must mention, that is of the types of units. Now units are of two types. The first one is the fundamental units. Fundamental units are those units which can neither be derived nor can they be resolved into other units. Now this means that all the fundamental units are different from one another because no one fundamental unit will ever depend on the other fundamental unit. Some examples of fundamental units are the meter, kilogram, second, Kelvin, ampere, candela. These are all examples of fundamental units. Now you can see from these examples that no one of these units depends on another. You can't describe the unit of meter by using the unit of kilogram and vice versa, and therefore there is no connection between any two of these units, and that's exactly why they are known as fundamental units. The converse of this, of course, is the derived units, and therefore it means that derived units are obtained by multiplying or dividing two or more fundamental units. Let me give you an example. In the formula F is equal to ma, if I write down the units of each of these quantities, it will be something like this. We know that a is acceleration, which is nothing but the change in velocity by time. Now therefore, I will write the units of velocity and time. But velocity itself is a change in the displacement versus time, and therefore delta v itself became delta s upon delta t. This gives me delta s divided by delta t square. Now even if you don't know any of these formulae, right now you can understand what I'm trying to say. Delta s simply represents the displacement, and therefore its unit will be meter. Delta t is nothing but the time, and its unit is second as given in the SI system. And therefore, I will now write down the units of each of the quantities on the right-hand side of the equation. We know that the quantity mass is given in units of kg because we are going to write down all our formulae now in the SI system. And therefore, the unit of mass in the SI system is kg. And on the other side, I have displacement divided by time square, and this will be meter per second square. And therefore, now it is guaranteed that the unit of force will be kg meter per second square. So what I have done is derived the unit of force by looking at the units of mass and acceleration. So I multiplied the unit of mass with the unit of acceleration, and I got the unit of force, which is kg meter per second square. This unit is actually nothing but the unit Newton. And therefore we know now that Newton is a derived unit because it is obtained by multiplying two other units. Now, so far we have described the systems of units which are internationally used, but sometimes even these units are not enough, and therefore we need what are known as practical units. This is because a large number of units are used in general life for measurement of different quantities in comfortable manner. They are neither fundamental units nor derived units, and such units are called practical units. These units may also include units which are used in daily life by normal people, but they are definitely not used by scientists. But that doesn't mean that they are useless. They are in fact practical units and definitely useful to understand the quantity of matter. So let's take some examples of practical units. Some of the examples of practical units of length is a light year. Why do we need this light year unit of length is because sometimes the distances at the scale of the cosmos are so big that we can't describe them in terms even of the kilometer. And therefore we need a very big unit of length, and one of the very big units of length is the light year. By definition, 1 light year is the distance travelled by light in 1 year. And therefore if I measure that in 1 whole year, how much distance has the light travelled, then that will come out to be 9.46 into 10 raised to 15 meters, and this is 1 light year. Another practical unit of length is the astronomical unit. 1 astronomical unit is the distance between the center of the Earth and the Sun, and this is nothing but 1.5 into 10 raised to 11 meters, and this is 1 astronomical unit. So you can imagine that if the distance between just the Earth and the Sun is so large, then the distance between our galaxy and another galaxy and the distance between different galaxies must be much larger than that. And this is the reason why we need these really big units of length. Another practical unit of length is then a parsec. 1 parsec is given by 3.26 light year. Already the light year was a very big unit of length, and now we have an even bigger unit of length, that is a parsec, which itself is 3.26 times the light year. And similarly, we also have practical units of mass. One of the most practical units of mass is quintil, which is given by 100 kg or 10 raised to 2 kg. Usually this unit is used to measure the weight of grains or rice, therefore it is used in agriculture. So 1 quintal is 10 raised to 2 kg. Another practical unit of mass is the metric ton. 1 metric ton is equal to 10 raised to 3 kg. We use the unit of metric ton to describe really heavy objects. For example, the Golden Gate Bridge is said to weigh 8,04,673 metric tons. And because of this metric ton, it is easier to say this number definitely as compared to saying it in kg. Of course, this number itself seems really big, and there definitely might be a bigger unit of mass that we can use to describe the mass of the Golden Gate Bridge, but you get the picture. Another practical unit of mass is the atomic mass unit. Now, we have already been talking about really big units, but this is an example of a very small unit. The atomic mass unit is the mass of one single atom. Therefore, 1 atomic mass unit is equal to 1.66 into 10 raised to minus 27 kg. And because atoms and molecules are really small, we definitely also need a unit of mass which is also very small, and atomic mass unit does exactly that. Now finally, we also look at some practical units of time. Now we can't always keep describing every measurement of time in terms of seconds. A second is a very small unit of time. Sometimes we need a big unit of time. For example, a year. We know that a year is nothing but the time taken for the earth to travel around the sun once. And therefore 1 year is 365 and 1 quarter day. That quarter is exactly why after 4 years, we have that 1 extra day in the leap year. So 1 year is 365 and 1/4 of a solar day. This is a big unit of time. Another big unit of time is 1 lunar month. This is given by 27.3 solar days. Another practical unit of time is 1 solar day, and this is written in seconds as 86,400 seconds. So these are the practical units of length, mass and time. Besides these, of course, there are a large number of other practical units that you must have seen in your daily life. So we saw that any physical quantity can be completely described by using its magnitude and the unit. But how do we actually find the magnitude of these physical quantities? We find it by using measurements. So we know that physical quantities are measured using some measuring instruments. But the question is, how do you decide the reliability of the instrument? That is, how can I be sure that the measurement that I'm taking is correct? And the answer to this lies in finding out some certain concepts. For example, we define what is known as the accuracy of an instrument. It is the closeness of the measurement to the true or the known value. So let me give you an example of what I mean by accurate measurement. Let's say that we have the ordinary ruler that we all know. We know that the smallest measurement that we can make with this ruler is 1 millimeter. Now suppose I have a grain of rice and I try to measure the length of this grain of rice, then I'll see that the length actually lies somewhere between 1 millimeter and 2 millimeter. So normally if a person is trying to take the measurement of the length of this grain, what they'll do is either say that it is 1 millimeter or 2 millimeter because they don't exactly know what lies in between. And in such a case, whatever measurement you make, whether you say it's 1 or 2 or 1.5 or 1.4, you're not going to be sure of it. And in such a case, then the measurement is not very accurate. And this is what we mean by the inaccuracy of a measurement. And therefore, it is crucial to know that the more close the value that you have measured is to the actual value, the more accurate the instrument is said to be. On the other hand, there is a very minute difference between what is accurate and what is precise. Precision is determined by the least count of the measuring instrument. We know that there are some measuring instruments like the vernier caliper and the screw gauge. And the least count of the vernier caliper is 0.01 centimeter, whereas for the screw gauge it is 0.001 centimeter. Which means that the vernier caliper can make the smallest measurement of 0.01 centimeter, and the smallest measurement that you can make with the screw gauge is 0.001 centimeter. So sometimes people ask a question like, which of these should we use? Why don't we always use the screw gauge? Why should we use the vernier caliper when we know that the screw gauge is more precise? We know that the vernier caliper is less precise and the screw gauge is more precise. So which instrument should you actually use? The answer lies that it depends on what exactly do you want to measure. For example, if I want to measure the distance between two cities, I'm not going to use a vernier caliper or a screw gauge, no matter how precise they are, because I'm not going to make measurements in centimeters, let alone 0.001 centimeter. I'll use something much bigger, a bigger unit of distance like kilometers to measure that. And then if I say that the distance between Mumbai and a different city is say 260 kilometers and you say that it is 261 kilometers, it's not that much of a difference. We are only off by 1 kilometer in 260 kilometers, which is not a lot. But if we both measure something that is 5 centimeters and then I say that it is 5 centimeters and you say it's 6 centimeters, that's a big difference. 1 centimeter out of 5 centimeters is a 20% difference in our readings. Therefore, how precise you want your measurement to be depends upon what you are measuring and what is the purpose of that measurement. And this is why accuracy and precision are two very different things. Now, most of the times what happens is that when you measure something, you usually have to round off. Just like we did with the length of the grain of rice and the ruler. We would have to round off either to 1 millimeter or to 2 millimeter. And then how to decide whether you are supposed to round off to 1 millimeter to 2 millimeter. So in such a case, what we have are some rules of rounding off. The first rule is that if the digit to be dropped is less than 5, then the preceding digit is left unchanged. For example, if you have a measurement like x is equal to 7.82, then the last digit 2, like I just said, is less than 5, and then you can just drop it and there is no change to the digit before it. And therefore, your final rounding off measurement is x is equal to 7.8. But however, if the digit that you have to drop is more than 5, then the digit before it is raised by 1. For example, if I have the measurement x is equal to 6.87, then in this case, the last digit which I want to round off is more than 5, it's 7. And therefore, the digit before it, which is 8, will be increased by 1, and my final answer will be x is equal to 6.9. Another rule is that if the digit to be dropped is 5, but it is followed by digits other than 0, then the preceding digit is raised by 1. So for example, if I have x is equal to 16.351 and I want to drop the 5, I first have to check whether the digit after it is 0 or not. Now as I can see, the digit is 1, which means it's not 0, and then if it's not 0, then the digit before it will be added 1, and then my answer will be 16.4. And then if the digit to be dropped is 5 and it is followed by zeros, then you have to check the digit before the 5, and if it is even, leave it unchanged. So for example, if I have x is equal to 3.250 and I want to drop the digit 5, but I have to check what is the digit after 5 and I see that it is 0, then I also have to check the digit before 5, and if it is even, then I have to leave it unchanged, and my answer is remaining as x is equal to 3.2. On the other hand, if again the digit to be dropped is 5 and again it is followed by zeros, and again when I check the digit before it, if that digit is odd, then you have to increase it by 1. So if I have x is equal to 3.750 and I want to round off to the first digit after the decimal, that means I want to drop 5, then I will check whether the digit after it is 0, which it is in this case, and then I check whether the digit before it is odd, and it is odd. And if it is odd, then I have to add 1, and then my rounding off measurement is x is equal to 3.8. So this was the different rules when I'm rounding off a measurement. But like we've already discussed, there could be errors in our measurement. There could be a human error, it could be an instrumental error. Overall, any measurement is subject to certain errors, and it is important to keep in mind what these errors are. So what exactly is the definition of an error in measurement? The difference in the true value and the measured value of any quantity is known as the error in measurement. If the grain of rice actually has a length of 1.15, but you have measured it as 1.1, then the error is the difference of these two values. So let's see what are the types of errors. To understand that, first remember that whenever you do a measurement, the best way to get a better result is to measure the same thing again and again. And therefore, let's say for example, when you're measuring same quantity multiple times, for example, if I'm measuring the weight of a substance using a very minute machine, and then when I weigh it the first time, I see that the measurement shows 10, and this I will record it as my first measured value, A1. But I will not measure it only once because I want a very accurate measurement. So what I do is I measure it again after some time, or I put the same quantity in a different container and measure it again, or I place it in a different room and measure it. So basically, I will measure the same quantity again and again, and I will see that the measurement is not always the same. So now in this case, I got a measurement of 10.05 and this will be A2. And similarly, what I will always get is a set of values. So whenever you're measuring a quantity, always obtain a set of values where you have measured the same quantity multiple times. These set of values we will call A1, A2 up to AN, where n is the number of measurements that you made for the same quantity. Once you have this set of values, I can now define what is known as the absolute error. Absolute error is the magnitude of the difference between the mean value and the measured value of the quantity. So for example, for this I first have to define what is the mean value. So if I want the mean value, I simply add all of these values and divide it by n, where n is the number of measurements I made. This gives me the mean value, which I denote as A subscript m. Now I said that the absolute error is the difference between the mean value and the measured value, which means if I wanted to find the absolute error in A1, which I will call as delta A1, then delta A1 is simply AM minus A1. As you can see, AM is the mean value and A1 is the measured value. And therefore, the difference between this will give me the absolute error in A1. And therefore, absolute error is actually defined for every single measurement. Similarly, then I can write down delta A2, which will be AM minus A2. And then I can write for all of the others, that is delta AN is equal to AM minus AN. So this is what I mean by absolute error. And from the absolute error, I can also find the mean absolute error, which is nothing but the arithmetic mean of the magnitudes of the absolute errors in all the measurements of the quantity. The point to note here is that I am taking a mean of all the absolute errors, but I am taking a mean of their magnitudes, which means that if I get a minus sign also in the absolute errors in the first case, I will ignore the minus sign. I simply have to take their magnitudes, add them all up and divide them by the number of measurements so that I get the mean absolute error, and this is given as delta A with a bar on top of it, and this is a magnitude that is always a positive quantity. From this now we can write down what we actually mean when we have a measurement. This means that whenever I have a measurement of a quantity, that measurement will always is likely to lie between AM plus delta A bar and AM minus delta A bar. This is the range of accuracy. So my measurement is lying between these two values. So this is the range of my measurement. The next type of error is the relative error or the fractional error. This is simply the ratio of the mean absolute error to the mean value. We already found the mean absolute error as delta A bar, and if you divide that by the mean value, that is A subscript m, this will give me the relative or the fractional error. And once we have the relative or the fractional error, then the percentage error is simply the relative error multiplied by 100, and therefore it is delta A bar upon A subscript m into 100, and this will give me the percentage error. We then move on to the idea of significant figures, and we must first discuss the order of magnitude. By definition, the order of magnitude of a physical quantity is defined as the value of its magnitude rounded off to the nearest integral power of 10. This means that any physical quantity can be expressed as P is equal to A into 10 raised to n, where A is a number between 0.5 and 5 and n is the integer which we call as the order of magnitude. So why is the concept of significant figures important? So significant figures in the measured value of a physical quantity is the sum of reliable digits and the first uncertain digit. For example, it has some certain rules. All non-zero digits in a measurement are significant. For example, if you have 24.123, all of them are non-zero and all non-zero digits are significant, and therefore this measurement will have 5 significant digits. The second rule says that a zero becomes a significant figure if it appears between two non-zero digits. For example, in 4.004, we see that there are 2 zeros between two non-zero digits. In such a case, those are also considered to be significant, and this measurement now has 4 significant figures. The third rule says that the leading zeros or zeros placed on the left-hand side of the number are not significant. That is, 0.006 has 3 zeros to the left of the number 6. In such a case, these 3 zeros are not significant and this measurement has only 1 significant figure. The fourth rule says that trailing zeros or the zeros on the right-hand side of the number are significant. So for example, if the measurement is 4.330, then the zero which is on the right-hand side is the trailing zero, and we are saying that this zero is significant and hence this measurement has 4 significant figures. And similarly now in another case, if I have 343.000, that is I have trailing zeros after a decimal, still these 3 zeros are still significant and they must also be counted, and therefore this measurement in this case has 6 significant figures. In exponential notation, the numerical portion gives the number of significant figures. For example, if I have 1.32 into 10 raised to minus 2 and 1.32 into 10 raised to minus 4 as two separate measurements, in this case, the exponential part is insignificant and the other part is the significant part, and therefore both of these have the same significant portion and these both have the same number of significant figures, that is, they both have 3 significant figures. So these were the rules of significant figures. The last thing that I want to discuss with you is the idea of dimensions. In mechanics, most quantities are written in terms of the dimensions of mass, length and time. And therefore, most of the quantities will have MLT as their dimensions. However, in heat and thermodynamics, an extra dimension of temperature is added and therefore most of them will have quantities like M, L, T and K. And in electricity and magnetism, instead of temperature, we have the fourth dimension of ampere or electric current, and therefore the dimensions are written as MLTA. So why is dimensional analysis even important? It is important because in dimensional analysis, the dimensions of any physical quantity can be expressed in the form of a dimensional equation. And the advantage of this is that it is based on the principle of homogeneity, which means that the dimensions of all the terms on either side of a physical equation are same. So how exactly can we use this to our advantage? For example, if I check the correctness of this equation, force is equal to mass into acceleration, then I know that mass has a dimension of m because it's only mass. Acceleration is actually meter per second square, that is length per second square, so I'll have L t raised to minus 2, and therefore I can be guaranteed that in this equation, force will have the dimensions of mlt raised to minus 2 because dimensional analysis is based on the principle of homogeneity. So let's write down what are the applications of dimensional analysis. The first one, like I said, is to check the correctness of a physical equation. Any physical equation is correct only if the dimensions of all the terms on both sides of the equation are same. For example, let's check if the equation v is equal to u plus at is correct. Let's write down the dimension for each of these terms. The dimension of the term u, which is the initial velocity, is nothing but length per time, and therefore it is m raised to 0, l raised to 1, t raised to minus 1. The dimensions of acceleration, which is nothing but displacement per time square, will be given by m raised to 0, l raised to 1 and t raised to minus 2, and time is simply time, so that's t raised to 1, and when I multiply the dimensions of acceleration and time, I get m raised to 0, l raised to 1 and t raised to minus 1. So you can see that the dimension of u and at are already matching. And therefore now when I check the dimension of v, which is also length per unit time, I will see that its dimension is m raised to 0, l raised to 1 and t raised to minus 1. And thus I can be guaranteed that because each of them have the same dimension, this equation is correct. The next application of dimensional analysis is to derive the relationship between physical quantities. For example, in case of a simple pendulum, we know that the time period of a simple pendulum depends upon the length of the simple pendulum and the acceleration due to gravity. Therefore, I can say that t is proportional to L and g. But I don't know whether they are directly proportional, whether it's proportional to the second power, the third power, or the first power. And therefore, to find this out, I will use dimensional analysis. So in general, I say that let it be that t is proportional to L raised to a and g raised to b, where a and b are the numbers that I want to find. Now what I will do is I will say that t proportional to L raised to a, g raised to b can be written simply as t is equal to k, L raised to a, g raised to b, where k is nothing but the proportionality constant. And this proportionality constant is dimensionless. And therefore now I will apply the dimensional analysis and say that length is simply length, and therefore its dimension should simply be L raised to 1, therefore m and t will just be raised to 0. But acceleration due to gravity, which is an acceleration, will be length per unit time square. And therefore I'll get L raised to 1, t raised to minus 2 and m is 0 as usual. Now once I have this, I can also write down the dimension of time, which is simply t raised to 1, and k has no dimension. Now I will do the dimensional analysis, and on the left hand side I see that I have the dimension of time, which is t raised to 1, and on the right hand side I will write down the dimension of L, that is m raised to 0, L raised to 1, t raised to 0, and raise this to a because I actually have L raised to a in my equation. I'll do the same thing for g, that is I will multiply it by m raised to 0, L raised to 1, t raised to minus 2 raised to b. Once I do this, I will actually multiply all the exponents by the exponential rules, and I will get that on the right hand side I have m raised to 0, l raised to a plus b and t raised to minus 2b. And then I will compare the exponentials on the left hand side and the right hand side and see that I have a plus b is equal to 0, minus 2b equal to 1, and this gives me that b is equal to minus half and a is equal to half. Now I put that back in my equation and I get that t is equal to k, l raised to half, t raised to half. And from experimental observations, I see that k comes out to be 2 pi, and this gives me the formula that is very famous, that is the time period of the simple pendulum. T is equal to 2 pi root L by G. And this is how dimensional analysis can help you find the relationship between different quantities. So this wraps up all the concepts that I want to revise under the chapter Physical World and Measurement. I hope this was a very informative video for you. Thank you for watching.